Hello, students. Welcome to the 40th lecture on particle physics. And the last three lectures, we have started discussing neutrino oscillation. And in the last lecture, we stopped at this point, equation number 20, where the expression is given for the oscillation probability of nu e that is transforming to nu mu, and let us start discussing physics of this equation. Therefore, what you are realizing that this equation, if you look at equation number 20, which is given in terms of the mixing angle, the difference in the mass against state square, the length which the neutrino has traveled, and the energy of the neutrino, it may be observed that in the two flavor case, only sine squared 2 theta and delta m square are responsible for all the kind of transitions between neutrinos of two different flavors for a fixed neutrino energy and for a fixed length. Length means how long the neutrinos are traveling. The same expression will hold good for any two other flavors of neutrinos, that is nu e to nu mu oscillation, or nu e bar to nu mu bar oscillation, or nu mu bar to nu e bar oscillation. Furthermore, probability of transition between the two flavor states would be the same for nu alpha to nu beta and nu beta to nu alpha. That we have seen is because of T. If we assume that CPT is getting conserved, then if Cp is conserved, then T has to be also conserved. Therefore, if you talk about in Cp, you talked about nu mu to nu E oscillation probability is the same as nu mu bar to E nu bar. And then when you are applying CPT, you have nu E bar to, with CPT, you have nu E bar to nu mu bar. Just I am talking about the T, then time reversal we are talking about, and we are saying that the oscillation probability for transition from nu mu to nu e is the same as nu e to nu mu, and therefore we are talking about this scenario with Cp and Cpt. In fact, it will be true for any two flavors among the three different flavors of neutrinos. Three different flavors means whether you talk about nu e nu mu, or nu mu nu tau, or nu tau nu e, or the same will be true for nu e bar nu mu bar, or nu mu bar nu tau bar, etc. Now for a definite L, the oscillation probability will vary with E, because you see, if your theta is fixed, your delta m square is fixed, but still in the parenthesis what you can notice, you have L and E, and therefore if you vary one of them, the other you have to tune, and that is what we are talking about, that for a definite L, the oscillation probability will vary with energy. Therefore, a proper choice of L corresponding to the energy range, or what energy of the neutrino you have, ensures proper sensitivity to the oscillation probability. And that is why I am telling you that if NOVA experiment has average energy of 2 JeV, then its length of a study will be entirely different than from T to K, where the average energy is 600 MeV. The length will be completely different. Or if you talk about a neutrinos who have got energy, say average energy of around 3 JeV, then it will have a different, it needs a different length to study neutrino oscillation. The different length to study neutrino oscillation means the travel from the production site to the detector site, the detector which is placed at a long distance. That is important. Therefore, the quantity in the parenthesis of equation 20 is a dimensionless quantity. You are talking about sine square of something, and this was delta m square L by 4e. And notice that we have spoken about this factor in the previous class, that if we stick to h cross and c, we have this expression. And if we stick to this, then we are getting a number with h cross c as 0.19733 GeV Fermi instead of 197.3 MeV Fermi, you can equivalently write GeV Fermi, because 10 power 3 MeV is 1 GeV, and therefore you are getting a value that is close to 1.27 delta M square L by E, where L is in kilometers, E is in GeV, and delta M square in electron volt square. This is the probability of oscillation for, say, nu mu to nu E, the part we are talking about, or nu E to nu mu, any two flavor scenario. And therefore, what we are saying that if we take 4 pi E by delta M square and call it by the name oscillation length with proper substitution of H cross and C, we can write it as 2.48 E in GVs, delta M square in EV square, and then that means when you are making this dimensionless, your length is in simply in kilometers. Therefore, what we are doing, see, deliberately we are saying that we are measuring energy in GV, and at the same time we are making it dimensionless. Then delta M square in EV square, we are making it dimensionless, and then we are saying that whatever that is left is in kilometers. This is what you can see from here. This is where we have written L oscillation, the length of the oscillation, as this quantity. And now that will become clear why we are talking about this guy, half sine square 2 theta 1 minus cos 2 pi L by L oscillation. And L oscillation is simply, you can say that this is E by delta M square, where E is in GV. And you see, when L by E is much smaller than 1 by delta M square, this is one scenario. L by E is of the order of 1 by delta M square. And the third scenario is L by E is much greater than 1 by delta M square. Therefore, this is what we are talking about. And this is delta M square by 4 L by E. This is the difference range that we are talking about. Therefore, Neutrino oscillation length should be either equal to or less than the source to detector distance. Otherwise, the oscillation will not be developed. Remember, L oscillation is E by delta M square. Therefore, this is what we are talking about. L oscillation, if it is E by delta M square, what we are talking about, that if it is L oscillation, oscillation probability versus delta M square L by E, curve for sine square 2 theta, say 0.83, shows no oscillation scenario in the region when 1 by delta M square is much larger than L by E. Threshold condition for oscillation, you see, few signals, few transformation, and then when L by E is much greater than 1 by delta M square, or we are meeting this condition, then what you are saying that there are many oscillations, and then that means you can take average of that and your result would be fantastic. Therefore, the important point is that when we are looking at this distance of how long these neutrinos are going to travel, what is the average energy of this neutrino, accordingly we find that where our oscillations will be most sensitive to and where we won't be able to see any oscillation. And that is the catch in any designing any accelerator experiments. And this is the general video for telling you that neutrinos are changing from one flavor to another flavor, from volleyball to basketball to lawn tennis ball to football, whatever you talk about, nu mu to nu E to nu tau and others. Therefore, the important point is that the quantity that determines whether oscillation has occurred or not, when the neutrinos of a particular flavor have traveled a distance between the source and the detector, that is pi L by L oscillation. And this we are writing in terms of 1 by 1.267 delta M square in EV square, L in kilometers, and E in GV. That is the catch. Therefore, this guy is very important to us. In figure 8, we have plotted the survival probability. That means a nu mu remains a nu mu versus delta M square by 4 times L by E, this factor for sine squared 2 theta 1 2 equal to 0.83, where it may be observed that you have in this region there is no oscillation, here you have a few oscillation, and in this case you have many oscillations, and that is why you are taking the average of. Therefore, if the detector is very close to the neutrino source, that means we are talking about this, there will be no oscillation. This is what we are seeing. Then the most sensitive region is when the L by E is much greater than 1 by delta M square. This region is said to be the necessary condition for the oscillation. And then when L becomes much larger than the oscillation length, several oscillations will happen, and the average of the oscillation probability would be the most acceptable measurement. Remember, the most acceptable measurement that we have talked about. This is the region. And the other point that we have made many times, that this is the survival probability of a particular flavor of neutrino, and this is the appearance probability of another flavor of neutrino in a two flavor neutrino oscillation. And the important point is that here the expression in the parenthesis is written when we are assuming that length we are going to measure in kilometers, energy of the neutrinos in GeVs, and delta M square in electron volt square. Now you can play with it, but at the same time you have to look at this number. The survival probability is measured by the disappearance channel. We are measuring the fraction of neutrinos of the original flavor that is left with. On the other hand, the transition probability is measured by the appearance channel. We are measuring the fraction of neutrinos of new flavor. Now the different parameters that we are talking about, one is the mixing angle. This is one of the two fundamental parameters of neutrino oscillation phenomenology. If theta is 0, I have told you that there will be no oscillation, and the flavor eigenstate would be the same as the mass eigenstate, and that means neutrino of a particular flavor will propagate from the source to the detector as nu alpha or nu mu. If theta is equal to pi by 4, then the oscillation are said to be maximal, and at some point, because this is sine square 2 theta, along the path between the source and the detector, all of the neutrinos of one flavor will oscillate into another flavor. That is another important catch, that when theta is equal to pi by 4, we are seeing that there will be a point where all the nu mu's will be converted into nu e's, or all the nu e's will get converted into nu mu. A non-zero value of theta signifies how much the flavor eigenstates are different from the mass eigenstate. This is what we are talking about, the mixing. And then we have another parameter, that is delta M square, and it governs the frequency of oscillation. As you can see that we have plotted the three different regions where we have 1 over delta M square as an important ingredient. For a two flavor neutrino oscillation, there will be two mass eigenstates, M1 square minus M2 square difference. For oscillation to happen, either one of the neutrino mass eigenstates should be non-zero, or the two mass eigenstates should be non-zero and non-degenerate. They cannot have the same energy. Therefore, there must be a finite value of delta M square. Either one is 0, another is finite, or both of them are non-zero, but at the same time both of them cannot have the same energy. That is why they have to be non-degenerate, since the probability of oscillation would be unchanged for delta M2 square changing to minus delta M12 square, changing the sign. Therefore, it does not tell whether M1 is greater than M2 or vice versa. Now, the other important point that we should talk about is the L by E ratio, because you see the expression that we have, this L by E is, therefore we have discussed delta m square, we have discussed this guy. See, this is pi by 4, and then this is pi by 2, and this is 1. This is 1 point, and then we are going to talk about this L by E, L in kilometers and E in GV. This is another important guy which should be discussed. Therefore, the transition probability depends periodically on the quantity L by E and describes neutrino oscillation. L by E ratio is the parameter which is in the control of experimentalists, because T2K people are using 600 MeV neutrino beam, and then they know where to place the detector to see the oscillation signals. And if one is using 2.5 GeV neutrino energy, then also those group should be able to tell that where the detector should be kept to have the oscillation signals for accelerator or reactor. See here, this will be true for accelerator and reactor experiments, because these two are man-made experiments. Otherwise, solar neutrinos or atmospheric neutrinos or supernova neutrinos or geoneutrinos, you don't have control on that. Okay, they are natural sources. These we are talking about the man-made sources where you can place the detector. Therefore, L is the distance between the source and the detector, and E is the energy of the neutrino. And if you look at that expression, the sin square L by E expression, you have a factor 1.267 delta m square L by E. That should be equal to 2n plus 1 pi by 2, because that is sin square of that. While the previous one was sin square 2 theta, this is sin square of that, and therefore we are writing it as 2n plus 1 pi by 2, where n can be 0 or 1 or 2, whatever you like. And then that means if you compare this, that means del m square L by E must be equal to greater than 1. And this is an important condition when we talk about the length between the detector and the source and the energy of the neutrino. This is the point which one has to consider. For example, if we take n equal to 0, corresponding to the first oscillation maxima, delta m square is this much, and L is 500 kilometers or say 1000 kilometers and 2000 kilometers. The first maxima should be observed respectively at the energy. Just put these values at E equal to 1.01 GeV, the other 2.02 GeV, and 4.04 GeV. Therefore, you are changing L, and corresponding E is changing to have the first maxima. Similarly, you can, to see the second maxima, your n will be 1. Accordingly, you can see that how many oscillations you can see in a particular neutrino beam. And this we have shown here for the 3 different lengths where a neutrino is getting produced, and then it is propagating in space. And this is the, on the x-axis is the energy of the neutrino, and on the y-axis you have the probability. And we are talking about 2 flavor neutrino oscillation. As you can see that really the oscillation probability is depending upon the length between the detector and the source. Here L equal to 500 kilometers, then L equal to 1000 kilometers, and finally we have taken a case when L is equal to 2000 kilometers. Thus, you can do it as a homework, write a Fortran code and use those values to get these numbers. Therefore, these are the numbers which one gets when one is talking about neutrinos of fixed energy, and then where to see the maximum oscillation of nu mu to nu e or nu e to nu mu, and that becomes important. Therefore, the frequency of oscillation is controlled by delta m square and is shown in figure 10, which is obtained using equation 24 for a constant length and mixing angle theta. This figure is a plot of the transition probability as a function of neutrino energy. Here we have taken 2 energies, 0.1 GeV and 5 GeV at constant length 2000 kilometers, and theta equal to 45 degree for the various values of delta m square. Because delta m square we have to determine through the experiments, and the best value of delta m square fitting or best value will give us the least chi-square, and that is why we are seeing that what delta m square will mimic by oscillation signals. It may be observed that delta m square is directly proportional to E, that we have seen. With the increase in delta m square, the probability curve gets shifted towards the higher energies. As you can see here, we have taken the different values of delta m square. This is 2.2 into 10 power minus 3 eV square, this solid line. This dashed line is with 2.5, and this dotted line is 2.8 into 10 power minus 3 eV square. You can see that it is shifted towards what we are saying, that with the increase in delta m square, the probability curve gets shifted towards the higher energies. This is what we are saying, that the probability curve is getting shifted towards the higher energies. Therefore, by looking at the oscillations, you can determine the value of delta m square. Then here we have shown the probability and length on the x-axis for the two different neutrino energies, and for delta m square equal to 2.5 into 10 power minus 3 eV square, and sine square 2 theta to be equal to 1. As you can see that for the different neutrino energies, these oscillation curves, the maxima and minima, are really different. And from here you can visualize that what should be the your energy of the neutrino, or what should be the length of the neutrino, that has the length to which the neutrino should travel to see the oscillation signals, and to determine from there delta m square and the mixing angle. So therefore the important point is delta m square and theta, they are unknown parameters. From the oscillation studies, the best fit values give us information about delta m square and theta. That is why in the plots that you will see in the lectures or in the research papers, you will find the point, or it gets encircled by different experiments, because different experiments put the different limits on these delta m square and the mixing angles. Now here in figure 11 we have plotted transition probability for the two values of energy, 1 JeV and 3 JeV, using delta m square 2.5 into 10 power minus 3 eV square and sine square 2 theta is equal to 1. The peak occurs at the oscillation length you can see that it is 992 kilometers and 2976 kilometers, which you can see by this. Therefore you can see that one is at 990 kilometers and another is at 297 kilometer respectively, which can be seen from figure 11. It may be observed that at some distance from the source, all the neutrinos of one flavor are converted into another flavor, whereas at some other length there is no oscillation. And then you have again another length where you have complete new mu's. Therefore you have full conversion, then there is no conversion, and then there is a full conversion, and that depends upon the oscillation length. It can also be observed from this figure that the transition probability depends significantly upon neutrino energy. That is, the oscillation probability is not the same for the two different energies. Now, similar to two neutrino oscillation scenario, we have three neutrino oscillation scenario, and here you will have the unitary matrix as the 3 cross 3 matrix, and here the one neutrino flavor will be represented in terms of 3 neutrino mass eigenstates, nu1, nu2, nu3, and that is why I told you in the introductory lecture that then you will have theta 1 2, theta 2 3 and theta 1 3 as the mixing angles, and similar to that you will have delta m1 3 square and delta m2 3 square, and then you obtain the expression for the transition probability. Therefore, in the next lecture we will just write the expression of for the transition probability in the three flavor neutrino case, and then we will discuss the latest results on these parameters of delta m square and the mixing angle, which have been determined by the various experiments. All the experiments I am talking about, whether solar experiment or reactor experiment or accelerator experiment or atmospheric neutrino experiments. Therefore, we will look at the different present values on these experiments and what is also information on the CP evaluating phase delta. Therefore, let us stop here. See you in the next class. Thank you very much.